In our previous session, we had seen about types of stability. Let us start off with the longitudinal static stability in this session. Longitudinal stability is also the most important static stability mode. In airplane design, wind tunnel testing and flight research, it usually earns more attention than lateral or directional stability. Static stability was divided into longitudinal, lateral, and directional. Now, static longitudinal stability will be going through the center of gravity, aerodynamic center, neutral point, moments about center of gravity, equation of stabilities, and static margin. In an aeroplane, the center of gravity CG is the point at which the aircraft would balance were it possible to suspend it at a point. As the location of center of gravity affects the stability, it must fall within specific limits that are established by the aircraft manufacturers. On small airplanes, the center of gravity location is identified as being a specific number of inches from the datum, and the center of gravity range is identified the same way. On large airplanes, the center of gravity is its range are typically identified in relationship to the width of the wing. Hence, it is the point of exact center around which the body may rotate freely in all the directions, and center of mass. If we consider an airfoil at an angle of attack, we can determine the pressure variation around the airfoil and calculate the aerodynamic force and the center of pressure. But if we change the angle of attack, the pressure distribution changes, and therefore the aerodynamic force and the location of the center of pressure and the moment all changes. So determining the aerodynamic behavior of an airfoil is very complicated if we use the center of pressure to analyze the forces. We can compute the moment about any point on the airfoil if we know the pressure distribution. The aerodynamic force will be the same, but the value of the moment depends on the point where the force is applied. It has been found both experimentally and theoretically that if the aerodynamic force is applied at the location of 1/4 chord back from the leading edge on the most low-speed airfoil, the magnitude of the aerodynamic moment remains nearly constant with angle of attack. Using the aerodynamic center as a location where the aerodynamic force is applied eliminates the problem of the moment of the center of pressure with angle of attack in aerodynamic analysis. So, for supersonic airfoils, the aerodynamic center is nearer the half-chord location. Wind tunnel model. We will be using this wind tunnel model which says consider a wing body model. The area and the chord of the wing are 0.1 meter square and 0.1 meter respectively. Now assume that a horizontal tail is added to this model. The distance from the aeroplane's center of gravity to the tail's aerodynamic center is 0.17 meter. The tail area is 0.02 meter square. The tail setting angle is 2.7 degree. The tail lip slope is 0.1 per degree. And from the experimental values we have downwash angle when the wing-body combination is at zero lift is equals to 0 and the change in downwash angle with respect to the angle of attack is 0.35. With this data, we will be calculating different values for the aeroplane model. Moments about the center of gravity. A study of stability and control is focused on moments on the aeroplane and moments on the control surfaces. The pressure and the shear stress distribution over the wing produces a pitching moment. This moment can be taken about any arbitrary point. However, there exists a particular point about which the moments are independent of the angle of attack. This point is called the aerodynamic center of the wing. The moment and its coefficient about the aerodynamic center is denoted by m with subscript AC and Cm with subscript AC respectively, where Cmac is similar to moment about the aerodynamic center divided by where Q infinity is the dynamic pressure and S is the wing area and C is along the chord of the wing. At zero lift, coefficient of moment at the aerodynamic center becomes coefficient of moment at the 1/4 chord when lift is equals to 0. This says that the value of the coefficient of moment at the aerodynamic center can be obtained from the value of the moment of coefficient about any point when the wing is at the zero lift angle of attack. For this reason, moment at aerodynamic center is sometimes called as the zero lift moment. The aerodynamic center is a useful concept for the study of stability and control. In fact, the force and moment system on the wing can be completely specified by the lift and drag acting through the aerodynamic center plus the moment above the aerodynamic center. Now, considering the complete aeroplane, though we are most concerned with the pitching moment about the center of gravity of the aeroplane, M with subscript CG. MCG is created by 1. Lift, drag, and moment along the aerodynamic center of the wing. Second, lift of the tail. Third, thrust. And fourth, aerodynamic forces and moments on other parts of the aeroplane such that the fuselage and engines. The moment coefficient about the center of gravity is defined as CmCg is equals to moment about the center of gravity divided by the dynamic pressure and wing area along the wing chord. Combining the preceding concept, an airplane is in equilibrium in pitch when the moment about the center of gravity is zero. That is, when moment about the center of gravity is equals to the coefficient of moment among the center of gravity is equals to zero, the aeroplane is said to be trimmed. Static longitudinal stability. Consider the aeroplane in steady equilibrium flight at its trim angle of attack. Suddenly, the aeroplane is disturbed by hitting a wind gust and the angle of attack is momentarily changed. There are two possibilities, an increase or decrease in angle of attack. If the aeroplane is pitched upwards, then the absolute angle of attack is greater than the trimmed angle of attack. If the absolute angle of attack is greater than the trim angle of attack, the moment about the center of gravity is negative. A negative moment is counterclockwise, tending to pitch the nose down. Hence, the aeroplane will initially tend to move backward its equilibrium position after being disturbed. If the aeroplane pitched downward by the gust, that is, when the absolute angle of attack is less than the equilibrium angle of attack, the resulting moment about the center of gravity will be positive, that is clockwise, and will tend to pitch the nose upward. Thus, again, we have a situation in which the aeroplane will initially tend to move backward towards its equilibrium position after being disturbed. Therefore, we have to notice that the absolute angle of attack is given with alpha A and equilibrium angle of attack is given with alpha E. Now let us consider two aeroplanes and the respective pitching moments as shown. The pitching moment curve is considered to be linear until the wing is close to stalling. Here, both the aeroplanes are flying at a trim equilibrium point B. Suppose the aeroplane suddenly encounters an upward gust such that the angle of attack is increased to point C. At the angle of attack denoted by C, aeroplane 1 would develop a negative nose-down pitching moment that would tend to rotate the aeroplane back towards its equilibrium point. However, for the same disturbance, aeroplane 2 would develop a positive nose-up pitching moment that would tend to rotate the aeroplane away from the equilibrium point. If we were to encounter a disturbance that reduces the angle of attack, say to point A, we would find the aeroplane 1 would develop a nose-up pitching moment that would rotate the aircraft back towards the equilibrium point. On the other hand, aeroplane 2 would develop a nose-down pitching moment that would rotate the aircraft away from the equilibrium point. On the basis of this simple analysis, we can conclude that to have a static longitudinal stability, aircraft pitching moment curve must have a negative slope. That is, change in coefficient of moment with respect to change in angle of attack should be less than 0. Another point that we must make is from the figure here. Here we see two pitching moment curves. Both are satisfying the condition for static stability. However, only curve 1 can be trimmed to a positive angle of attack. Therefore, in addition to having static stability, we also must have positive intercepts, that is, coefficient of moment is greater than 0 to trim a positive angle of attack. In this case, the requirement for static stability would be dou Cm by dou Cl is less than 0. Hence, two conditions are related by the following expression here, which shows that the derivatives differ only by slope of a curve. Now, considering the wing body tail wind tunnel model, let us see how longitudinal static stability is applicable. This is the equation clearly shows the powerful influence of the location h of the center of gravity and the tail volume ratio Vh in determining the longitudinal static stability. According to the equation, the small letter a is the lift slope of the wing, body, tail, aircraft. H is the center of gravity in fractions of chord length. H subscript AC, WB, where AC stands for aerodynamic center and WB stands for wing body. And H is the center of gravity from the leading edge. VH stands for tail volume ratio. AT stands for lift slope of tail. A stands for lift slope of complete aircraft. Dou epsilon by dou alpha is the change in downwash angle with respect to angle of attack. The necessary criteria for the longitudinal balance and static stability are: 1. The coefficient of moment must be positive and the instantaneous rate of change of coefficient of moment along the center of gravity with respect to the change in absolute angle of attack must be negative. Both conditions with the implicit assumption that the equilibrium angle of attack falls within a practical flight range of angle of attack. First, we need to calculate the lift slope, where A, lift slope of WB. WB is the wing body. We have change in coefficient of lift to the change in angle of attack. Substituting the values, we get 0.083 per degree. We assume that the aircraft lift slope of the wing body is equal to the lift slope of the aircraft. So, A subscript WB is equal to A. Now we have to find the moment coefficient about the center of gravity with respect to the wing body combination. So CmCgWb is equals to moment coefficient about the aerodynamic center with respect to the wing body combination plus the slope of the lift curve and absolute angle of attack with respect to the wing body tail combination, and multiplied by the lift acting through the moment arm H minus H of aerodynamic center with respect to the wing body combination. So in this problem, we have alpha is equals to 1 degree and 7.88 degree, and the moment of coefficient about the center of gravity are measured as minus 0.01 and 0.05 respectively. So evaluated at angle of attack of 1 degree, remember that alpha is the geometric angle of attack, whereas alpha WB, that is alpha with respect to the wing body, is the absolute angle of attack, because of which we have to add 1 plus 1.5. So we get this equation, and evaluating at alpha is equals to 7.88, we get 0.05 is equals to Cm alpha, Cm at aerodynamic center with respect to the wing body plus 0.08 into 7.88 plus 1.5 into the wing lift acting through the moment arm. The preceding two equations have two unknowns, that is coefficient of moment and the H minus H of ACWB. They can be simultaneously solved and subtracted to get minus 0.06 is equals to 0 minus 0.55 into H minus H ACWB, which gives H minus H ACWB is equals to 0.11. Now to find the tail volume ratio VH, we have LTST is the volume characteristics of the size and location of the tail, and CS is the volume characteristics of the size of the wing. By substituting the values, we get 0.34. And we note that lift slope of tail is 0.1 per degree, which is already given in the description, and change in downwash angle with respect to angle of attack is 0.35. Substituting all this in the equation of static longitudinal stability, we get minus 0.0133, which says the slope of the moment coefficient curve is negative, hence the aeroplane model is statically stable. Is the model longitudinally balanced? To answer this, we must find the coefficient of moment, which is combination with the preceding result, to find the equilibrium angle of attack. So here we have Cm naught is equals to Cm, that is coefficient of moment along the aerodynamic center with respect to the wing body, plus the tail wing ratio into the lift of tail into tail setting angle plus downwash angle when the wing body combination is at zero lift. By substituting the following equation from the before problem, we get Cm along the aerodynamic center wing body is equals to minus 0.032 IT is equals to 2.7, that is tail setting angle is equals to 2.7 degree. Substituting all the numbers here, we get Cm0 is equals to 0.06. Equilibrium angle is obtained by coefficient of moment at zero angle of attack minus change in coefficient of moment along the center of gravity divided by change of absolute angle of attack into the equilibrium angle of attack. So we get 0 is equals to 0.06 minus 0.0133 into the equilibrium angle of attack, which is equals to 4.5. Hence, this angle of attack falls within the reasonable range. Therefore, the aeroplane is statically and longitudinally stable. Neutral point. Consider the situation where the location H of the center of gravity is allowed to move with everything else remaining fixed. The static stability is a strong function of H. Indeed, the value of dou Cm Cg by dou alpha A can always be made negative by properly locating the center of gravity. In the same vein, there is one specific location of center of gravity such that dou Cm Cg by dou alpha A is equals to 0. The value of H when this condition holds is defined as the neutral point denoted by Hn. When H is equals to Hn, the slope of the moment coefficient curve is 0. For an aeroplane design, neutral point is a fixed quantity. For longitudinal static stability, the position of the center of gravity must be in forward to the neutral point. Let us consider a wing body tail example for this neutral point too. So Hn is equals to H at aerodynamic center with respect to the wing body plus the tail volume into lift of tail divided by the lift of aircraft into 1 minus change in downwash angle with respect to angle of attack. So from the previous exercise, we got to know that H minus H ACWB is equals to 0.11. and HACWB is equals to 0.35 minus 0.11, which is equals to 0.25. And wing volume of tail is equals to 0.34, and lift slope of tail is equals to 0.1 per degree, and lift slope of complete aircraft is 0.08. And change in downwash angle with respect to angle of attack is equals to 0.35. So substituting all this in the neutral point equation, we get Hn is equals to 0.56. So the center of gravity location H is located at 0.35. Comparing this with the neutral point location Hn of 0.516, which indicates that the center of gravity is forward of neutral point. Hence, the aircraft is statically stable. Static margin. If an airplane encounters disturbance in pitch causing an increase or decrease, the aerodynamic forces on the aircraft causes the decrease or increase in angle of attack. This is longitudinal stability. Static margin is used to characterize the static longitudinal stability and controllability of aircraft. Static margin is the distance between the center of gravity CG and the neutral point. If the CG is ahead of neutral point, it is positive static margin, and if CG is behind the neutral point, it is negative static margin. Let us see a wing body tail example for this too. We know that Hn is equals to 0.516 and H is equals to 0.35. So subtracting these two, we get 0.166. Static margin must be positive. More the static margin, larger the stability and more stable the aircraft. Hence, we get dou Cm Cg by dou alpha A is equals to minus A into static margin. We get the answer as minus 0.0133 degree. Static margin is direct measure of longitudinal stability. By this, we have come to the end of the longitudinal static stability. Let us start off with the lateral static stability in the next session. Thank you.